Okay, so welcome everybody. Good evening on this very lovely day. My name is Ellen Pristak. I am the coordinator of the Great Minds Salons. It's been a really great year. We've had some wonderful presenters, and I think our final presenter tonight will be way out of this world. I'd like to tell you a little bit about Josh. Josh Winn is a professor of astrophysics at Princeton University. He and his family, his wife Laura, and their two children, Sam and Sophie, who you know I like to claim when I know them, former students of mine, moved to Princeton and joined the Jewish Center in 2016. Previously, they lived in the Boston area, where Josh had been a professor at MIT. Josh has recorded 2 lecture series about astronomy for the teaching company and their streaming service, Wondrium. Okay. And is writing the little book of exoplanets. This one's a challenge. To be published by Princeton University Press. That one I got out okay. So I'm thrilled to welcome Josh. If you have questions during Josh's presentation, please put them in the chat and he will answer them as he gets the chance. So Josh, I'm going to turn it over to you. Everybody, please enjoy. I know we will.
Thank you, Ellen. Thanks everybody for coming out tonight. I want to talk to you tonight about exoplanets, and I think I should start by saying what that is. So an exoplanet is a planet, but it doesn't go around the sun. It goes around a distant star, one of the stars in the sky. In fact, let me start my slideshow. So if all has gone well, you're now looking at the night sky. We see countless stars. Each of those stars is a sun, and it seemed likely for many years that those suns probably have planets of their own, and that's what we mean when we are talking about exoplanets. So this is a very exciting, very rapidly advancing field, and it's been a lot of fun to be part of it. And I've given a lot of lectures about this over the last couple of decades now, and usually I emphasize the science. I talk about the technology that we use and the physics of planet formation and lots of stuff that, frankly, is usually interesting only to scientists and engineers and that sort of person. So for tonight, I decided to do something a little different. I asked myself, before I was studying exoplanets, in fact, even before I was a scientist at all, when I was a child, what would I have wanted to know about planets around other stars? And the answer is not the physics of planet formation. The answer is Luke Skywalker's planet real? What about Star Trek? What about all those planets? Are there planets like those somewhere out there? So that's what we're going to do tonight. We're going to do science versus science fiction. And along the way, I'll tell you a little bit about how we know what we know. All right, ready? Here we go. Okay, I guess that's enough of that, Ms. Chagas. Let's now get on with the problem. Why has it taken so long to find planets around other stars? What makes this problem so difficult? And the first problem is simply that the stars are very far away. So if we were to shrink the sun down to the size of a grapefruit, then the Earth would be about 40 feet away from that grapefruit. And the very nearest star would be about 2,000 miles away. So it's ridiculously far away. It would take tens of thousands of years even to reach the nearest star with our fastest available rockets today. So for the time being, visiting these planets is completely out of the question. And the only information that we are going to get is what we can see through our telescopes, the information that we can obtain from the trickle of light that happens to be directed towards the solar system and the Earth. So that's the first problem. We're going to have to rely on telescopes. The second problem is that planets are much smaller than stars. So Jupiter is a tenth of the size of the Sun. And then the little puny Earth down here is another factor of 10 smaller than Jupiter. And that's going to make planets very difficult to detect relative to stars. Even worse, and something that is really impossible to represent in this picture, is that planets are much fainter than stars. So the Earth, for example, is only reflecting a tiny fraction of the sun's light. And if you were trying to view the solar system from far away, the sun would be about 10 billion times brighter than that little dot that represents the Earth. And it's very difficult to make out such a faint dot in an image. In fact, the reason I'm showing you this slide is to order of magnitude. It's the same problem as trying to detect a firefly that is buzzing around in the vicinity of a powerful searchlight, and you have to do that from thousands of miles away with your telescope. So it's bordering on the impossible, like not quite impossible. And at the end of this presentation, I will show you one example in which this direct method of making an image of a planet has actually worked. But it's unique. And most of the time, and almost all of our information about exoplanets comes from more indirect methods. Okay, so first science fiction world we have to come to terms with is in the southern sky. So this is an image of the sky as viewed from Australia or somewhere down south. Here's the famous Southern Cross. This is the constellation of Centaurus that curls around it. And over here are the two stars in the Alpha Centauri system. This is the nearest star system to the sun. They are only about 4 light years away from our solar system. So this, because of its proximity, Alpha Centauri is in all kinds of science fiction stories. It's sort of the first destination for any type of civilization on Earth that can imagine traveling through space. So for example, that's where the astronauts were headed in Lost in Space. That's where the planet was in Avatar. It was a moon around a planet surrounding one of the two stars of Alpha Centauri. So we have to know, are there planets around Alpha Centauri? And unfortunately, the answer right now is we don't know. We have not yet detected securely any planets around Alpha Centauri. So that's disappointing. On the other hand, if we go back to this image of the sky, there is another star here, Proxima Centauri, that is not as well known. You can't even see it with your naked eyes. It's too faint. But it is slightly closer to the Earth than the two stars of Alpha Centauri are. It's ever so slightly closer. That's why it's called Proxima, for nearby. And we do know of a planet around Proxima Centauri. And what's even more exciting is this planet, which has been called Proxima b, is located within the star's so-called habitable zone. The habitable zone is the range of distances from the star where the warmth from the star is sufficient to allow water to exist as a liquid on the surface of a rocky planet, as opposed to vaporizing if you're too close to the star or freezing if you're far away. And the reason why this is called habitable is that we think that liquid water is and was essential for life on the Earth. And so if we're going to look for life on other planets, we should probably prioritize the planets that have liquid water oceans, that is where you could go for a swim. And so finding a planet comparable in mass to the Earth, located within this star's habitable zone, was a very exciting discovery. I think it was announced, I don't know, something like 5 or 6 years ago. Front page news. If you do remember that announcement, it was probably accompanied by this astonishing image from the surface of this new planet. It shows this kind of valley. There's some mist rising in the valley. There's the Proxima on the horizon. You can even see Alpha Centauri in the distance. Of course, this is a complete fantasy. We have no idea what it looks like on the surface of this planet. Everything we know about this new planet is contained on this chart. This doesn't look like a picture of a planet, so what is this chart all about, and how do we know that this chart implies the existence of a planet? What we're showing is speed versus time. What does that have to do with anything? What does that have to do with a habitable zone planet? So let me explain. We have to be sneaky. We can't just make images. We can't just take a picture of the star and hope to see the faint planets going around it. Contrast is too high. So we have to use our knowledge of basic physics and measurement techniques with light to deduce the existence of these planets, even though we cannot see them. And in this case, the trick is based on the fact that when we say that a planet is orbiting a star, that's actually not exactly right. Really what's happening is that both the star and the planet are going around their common center of mass. That is the average position of all of the bodies in the system weighted by mass. So because the star has such a higher mass than the planets, the center of mass of the planetary system is very close to the center of the star. But it's not right at the center of the star. It's displaced a little bit. And so the sun, for example, is moving around the center of mass of our solar system. The same should be true of other planetary systems. And that's what gives us our way in. Because we have gotten very good at seeing the motion of stars. The way it works is the Doppler effect. So you might have, I'm sure you've heard that term at some point, but just in case you need a reminder, this is the Doppler effect. So the Doppler effect is what you get whenever you have a moving source of waves. In this case, it was a car that was generating sound waves. When the car is moving, it's catching up with the waves that it's emitting in the forward direction. And so if you're viewing it from over here, seeing these waves come in, you will see the space between those waves have a shorter length than it usually does. In other words, the wavelength is compressed. And in sound waves, that means that you will receive a higher pitch. Whereas on the other side, if you're viewing the car from over here, the wavelength will appear to be longer than usual, and that means a lower pitch. So that's why the car sounds like the pitch drops as the car changes from approaching you to receding in the other direction. So that's the Doppler shift. It happens for any kind of wave, including light waves. So if that car has headlights and it's moving towards us, the wavelength of those light waves will appear to be smaller than usual. And for light, that means, it doesn't mean higher pitch, it means bluer. It's shifted toward the blue end of the spectrum. Whereas if the light source is moving away from us as the car is receding, its light should look slightly redder because it's been shifted to longer wavelengths. Now we never noticed that. The cars don't look any redder when they're speeding away from us. And that's because it's a very tiny effect. You have to divide the speed of the source, the car, by the speed of light. And so that's a very tiny number to give you the fractional change in wavelength. But as astronomers, we have developed very precise technologies for monitoring the Doppler shifts of stars. And so we can tell when a star is moving around the center of mass of a planetary system. So that's why this chart was showing speed against time. It's the speed of the star as gauged from the Doppler effect towards or away from us over time. And so the evidence for the planet is the fact that these data points, these red points, don't just sit here at zero speed, but they seem to oscillate back and forth and back and forth. That is the star orbiting around the center of mass of its planetary system. And from the period of this oscillation, how long it takes to make a complete cycle, that tells us the orbital period of the planet, how long it takes to go around the star. And from the amplitude, the amount, the maximum speed and the minimum speed, that tells us something about the planet's mass. In fact, it tells us the minimum possible mass for that planet. So that's how we know that there is a planet located in the habitable zone of this nearby star. So that's very good for science fiction. It means that authors can justifiably send their spaceships to Proxima Centauri and have them land on a potentially habitable planet. This is another famous chart in this field. This is also the Doppler shift, but it's of a different star called 51 Pegasi b. And what is special about this one is it was the first one to be detected, the first object that everybody agrees is an exoplanet around a sun-like star. It was announced in 1995, and it was this detection that earned its two discoverers, Michel Mayor and Didier Queloz, 1/2 of the Nobel Prize in Physics in 2019. The other half, by the way, was won by our Princeton colleague, Jim Peebles, for his work on cosmology, on the Big Bang, but that's another story. All right, we're getting a little too serious here. Let's get back to science fiction. Star Wars. In the third episode, I believe, it ends with this climactic lightsaber duel between Anakin Skywalker and Obi-Wan Kenobi. And it takes place on a planet covered with lava, Mustafar. Could there be planets out there that have oceans of lava covering half the planet's surface? The answer is yes. We actually have pretty good evidence that these lava worlds exist. But to show you the evidence, I need to explain the other one of our two most productive techniques for detecting exoplanets. It's based on so-called transits. Okay, so what I'm going to show you now is a movie that was obtained on June 6th, 2012, which happened to be a day when Venus went directly between the Earth and the Sun. And if you were watching with a special filter, you can actually see the little black dot of Venus's silhouette traveling across the face of the Sun. So that's pretty cool. For exoplanets, that kind of thing must happen. I mean, sometimes a planet's orbit must carry it directly along the line of sight between us and that star. Now, we can't hope to make a movie like this. We would never have the resolving power to actually see that little silhouette go across the face of the star, but we can still tell that it is happening, even if the star is so far away that it appears simply as a point of light, because the star will appear to get fainter. Its brightness will go down by a little bit because the planet is blocking some of the light. So Jupiter going in front of the Sun, for example, would block about 1% of the Sun's light. And the Earth going in front of the Sun is about 100 parts per million. So it's a very small amount of light that it's blocked, but nevertheless, as astronomers, we've gotten very good at monitoring the brightnesses of stars as precisely as possible. And so this gives us another way to detect exoplanets, and that brings us to this lava world. So this is another chart. We're not seeing speed versus time though. This is the drop in brightness. That is, the star got a little bit fainter over time. And what we see is the star got fainter by about, 220 parts per million. That tells us about the size of the planet. If the Earth blocks 100 parts per million, and this one's blocking 220, it means it's something like 40% larger than the Earth is. So it's probably a rocky planet, somewhat larger than the Earth. Then the time axis tells us something interesting. So there was a dip here, and then there was another one over here at about 8.5. Then we look over here to see the units, and it's in hours. So this planet goes around the star every 8.5 hours, instead of taking 1 year like the Earth does. That tells us immediately that this planet is extremely close to the star that it orbits. To have such a very short orbital period, it must have a really tiny orbit and be moving very quickly. So that tells us about the planet's orbital distance, how far away it is from the star. And that already suggests that this is going to be a very, very hot planet. In fact, we can do better than that. We can measure the temperature of this planet. How can we possibly do that? Well, some of you have probably already noticed, if you're looking carefully, there's a second dip here in between the two main dips. So what is that all about? What's happening there is that, here's a little movie to fire up our imaginations. The planet goes in front of the star, and that's why we get this big main dip here. But then what happens is that the planet leaves the star, and its hot, illuminated day side comes into view. The hot side of the planet comes into view, and then it's kind of like a moon that's growing in phase from first quarter to now it's kind of a gibbous phase. So we're seeing a lot of the planet's hot, bright day side. But then it disappears. We lose it when it goes behind the star. That's what this second dip is here. The brightness rises gradually as the planet's hot day side comes into view and then drops when the planet is hidden by the star. So this is a so-called occultation. And by measuring how much light is lost during an occultation, we can tell how much light the planet was contributing to the total, which in turn depends on the temperature of the planet. How hot is it? That determines how much it glows. And so through means like this, we know that the temperature of this planet is more than 2,500 degrees Celsius or something like that, certainly hotter than the melting point of most common rocks and minerals here on the Earth. So it really is a reasonable inference that this is a rocky planet, comparable in size and mass to the Earth, that has, at least on its day side, oceans of lava. But really all we know about it is the size. We know the mass of this planet from the Doppler effect. We also know the temperature of this planet. So we really only have those three numbers, and the rest has to come from our understanding of physics. However, when we hand those three numbers over to our friends, the space artists, this is what they tell us is happening on the surface of this planet, which is known as Kepler 78. Okay, now I want to show you the data first, and then we'll talk about which science fiction planet it is. So this is, again, brightness versus time. And up here, we're seeing the data without any, just as they are. And then down here, we're getting a close-up of the region right around 1 here. So what's happening? Over time, over the space of like a month, the brightness dropped, and it went all the way down to 0.83. That is, 17% of the star's light was blocked during this event. That's way too big to be a planet. So that's interesting. Then over here, it dipped again by even more, and it went down to more than to less than 80% of its usual brightness. And then it repeated, and then it seems to keep repeating. But then if we zoom way, way in here, we see that there was another dip, much smaller dip, that was only about 1 part in 1,000. And that is of the right amplitude to be from a planet going in front of it. So what's going on here? There seems to be 3 different kinds of eclipses or transits, only one of which could be a planet. Well, what's happening is that we have 2 stars in this system, and we are viewing it from the side. And those 2 big dips were the stars eclipsing each other. The red star goes in front of the yellow star star goes in front of the red star. And in addition, there is a planet, hopefully you can see it on your screen, whose orbit is looping around both of those stars at the same time. So this is a planet with 2 suns in the sky. Does that remind you of anything? This is Tatooine. This is Luke Skywalker's home planet. So this particular planet is probably a gas giant, the one for which I showed you the data. But nevertheless, we do know that at least big planets, the kind that are easiest for us to detect, are quite common around pairs of stars. And pairs of stars are also very widespread. Something like half or more of the points of light that you see in the sky are actually double stars, binary stars. The sun doesn't happen to have one, but it's a very common pattern that we see in the galaxy. So that's exciting. Here's a diagram that shows the geometry of the Kepler 16 system, the first of these circumbinary planets to have been discovered. There's 2 stars going around, and there's a giant planet. I think it's comparable in mass to Saturn, going around both of them, inside of what would be the size of Earth's orbit around that same star. And my favorite is Kepler 47, because we have 2 stars at the center, but we know of 3 planets that are orbiting around this double star. And they kind of occupy positions like Mercury, Venus, and the Earth around this same star. So all of those, any creatures on these planets really would enjoy a double sunset. Okay, I don't know how many, this is a book that's not quite as popular around here. It's by Liu Cixin. It's called The Three-Body Problem. It's a great science fiction story. It's kind of mind-bending. And it involves, it's kind of weird, I mean, it's hard to summarize, but the basic premise is, what would life be like? What would a civilization be like on a planet that was in a chaotic planetary system, where the gravitational forces were so complicated because there was more than one star, there's lots of nearby planets, that the system was unpredictable. And at any moment, a planet could be ejected into space or fall onto one of the stars. What would civilization be like? So if that intrigues you, you should seek out this book. In fact, it's a trilogy now, and read all about it. So do we know of any planets that are in chaotic planetary systems? Here the answer is a qualified yes. And nothing quite as outrageous as what Liu Cixin imagined, but we do know of a planet in a very chaotic planetary system. It's called Kepler-36. It was discovered through the transit method. And here is a scale model of the star and the sizes of the two known planets' orbits. So these are very closely packed around the central star, for one thing. They also have orbits that are very similar in size to one another. That means they get close to each other. When the inner planet laps the outer planet, they have a close encounter and pull hard on each other. The planets themselves, to see on the same scale, we would have to zoom in a factor of 50. One of them is comparable in size and mass to the Earth, the other one to Uranus or Neptune. And so when they get close to each other, they pull on each other because of their own gravitational forces, and that introduces a randomizing effect in this planetary system. And that renders it unstable. So you may have heard of the butterfly effect. It's the idea that when you have a system with lots of strongly interacting parts, like the weather or like a complicated planetary system, then the future of the system depends extremely sensitively on the starting condition. And if you were to, say, have the butterfly flap its wings close to one planet rather than the other planet, then in the future, that effect would cause a major difference in the locations of those planets over time. Or in the case of the weather, if a butterfly flaps its wings in the Philippines, then that would create eventually uncertainty in the weather in North America, for example. So this is a chaotic planetary system. What it means is that it is intrinsically unpredictable. Actually, the solar system is unpredictable too. Any system with more than just one star and one planet is officially chaotic. However, for the solar system, the chaos doesn't set in until about 10 million years. That is, we can predict the locations of the planets very accurately out to a few million years bordering on 10 million years. If you ask me where the planets are going to be 500 million years from now, nobody knows. We just don't know the locations of the planets accurately enough. And that's kind of academically interesting. But for Kepler-36, the descent into chaos is about 10 years. So it's much faster because of the strong gravitational interactions between these planets that approach each other so closely. So any creatures on these planets really would have a hard time predicting the locations of the planets on timescales relevant to their civilization. So it makes you wonder, like on the Earth, the whole scientific revolution was ignited because people saw the motion of the planets, and it turned out to be a relatively simple, well, less complicated than many, physics problem that people could seize on and use to understand the laws of physics and inertia and so forth. There was this demonstration in the sky. If there were no such demonstration, if the planets were moving much more chaotically, like, would we have had a scientific revolution? Would it have just taken much longer? These kind of things are fun to think about, and we actually have a real-life example to ponder. Okay, another famous star is Canopus. So Sirius, which is a more famous star, is the brightest star in the night sky. That is the brightest star besides the sun. But Canopus is number 2. It's just that we can't see it from here in the northern hemisphere. You have to travel further south to get it to rise high above your horizon. And Canopus is also famous in science fiction because it is the home star of the planet Arrakis from Dune. It's the planet that has these sand dunes and is permeated by these purple worms that cause a lot of damage. Anyways, the reason it's so hot is presumably because Canopus is a giant star. It is much more luminous than the sun. And so even if a planet used to be like the Earth, by the time a star swells up and becomes a highly luminous giant star, it would become very, very hot and essentially or borderline uninhabitable, like Arrakis. So do we know of any planets around giant stars? The answer is yes. We do know of some planets around giant stars. Not Canopus, though. It turns out giant stars are much more difficult to search than stars like the sun, and it's for 2 reasons. One is that they're huge. A giant star might be 100 times larger than the sun. That makes the transit method very difficult because it means that a given planet will block a much smaller fraction of the star's light. And the other reason, the reason that interferes with the Doppler method, is that the surfaces of these stars are not stable. They pulsate more than the sun does. And that interferes with our ability to measure these tiny Doppler shifts due to the star's orbital motion. I've got a question that looks interesting. So in the case of a planet orbiting a binary star, would the planet's orbit be influenced in an erratic manner depending on where the orbital? Yes, the answer is yes. So because in systems like Kepler-16, the Tatooine-like planet, because the stars are always shifting in their positions, it means the gravitational force on the planet is also kind of jiggling around erratically. However, in that case, as long as the planet's orbital distance is more than 3 or 4 times the distance between the stars, nothing dramatic tends to happen. It's true, the shape of the orbit of the planet will jiggle around. It'll become more and less circular with time, but it won't be ejected, it won't fall onto one of the stars, as long as it's at a safe distance from the 2 stars that are going around each other. Let's see, so giant stars, very difficult to find planets around. We do know of a few. Let me just, for those of you who don't know, let me tell you what a giant star is. What am I talking about? So here is an animation, a kind of artist's impression of what the past and future of the sun would look like. So here we are in the past. The sun is in the middle here, and it is still surrounded by this vortex of material left over from its formation. And the planets form within this vortex. So let's let that happen. Okay, so now the disk, this vortex goes away, and we're left with some planets that are going around the star. And the sun does that and is happy for a long time. But after a few more billion years, it runs out of hydrogen in its core. And lots of non-obvious things happen at that point. It's not at all obvious why this should be the case. But when a star runs out of hydrogen at its core, it starts kind of burning out of control. There's still hydrogen burning within the star, but it's no longer at the core. It's a little higher up. That turns out to be unstable. It gets out of control and causes the star to puff up to many times its original size and become much more luminous. And that's a giant star, or a red giant star, because the surface of the star also becomes more red. So those are the stars for which we know relatively little about the planets that might still be orbiting them. However, if we let the movie keep going on, the radiation from within this red giant star gets so intense that the star ends up puffing out its outer layers into the surrounding space. So it unbinds itself, and what's left over is a very dense, hot core that's in the middle. So that becomes exposed to the rest of the universe at this phase, and we call that dense, hot core a white dwarf star. So they're very exotic. They have about half of the mass of the original star, but instead of being as big as the sun, they're about as big as the Earth. So they are very compacted to have an average density of around 1 million grams per cubic centimeter, so 1 million times more dense than water. So these are very exotic objects, and you might think it would be even harder and weirder to find a planet around a white dwarf star, but we actually have one. There was one that was detected. So let me show you the data. This is again through the transit method. So we're looking at brightness against time. What we see in this case, though, is that the brightness goes down by more than half. So it goes down below 0.5. So this planet is larger than the star it orbits. The star might be the size of the Earth. This planet is evidently larger than that. And we also see the duration is very short. So this only lasts about 8 minutes in total. It goes from -4 minutes to +4 minutes. And that tells us that the object being eclipsed is very small. That's part of the evidence that this really is something that is eclipsing the white dwarf star. This other panel is the same kind of observations with a different telescope. The agreement between the two panels was part of the evidence that this really is a planet as opposed to something else. So anyways, if we hand this off to our friends, the space artists, this is what they tell us we might expect as we approach in our spaceship. This is a star whose planet is probably comparable in size to Jupiter, from what we can tell. And yet it is orbiting a much smaller star. And furthermore, it's orbiting very closely. So it's well within what the Earth's orbit would have been like around the star, well within what Mercury's orbit would have been. So this planet could not have formed here when the star was a normal star. It would have been completely engulfed by the star. So somehow, this appears to be a planet, a giant planet, that survived even when its star became swollen and became a red giant, and puffed out its atmosphere and became a white dwarf, and then somehow, through a process we really don't understand, spiraled inward or got transported inward to take up a tight orbit around this kind of retired star, the white dwarf. So there's a lot of mysteries that this system opened up for us. Okay, black holes. So I don't know, many of you may have seen the movie Interstellar, very cool movie, Christopher Nolan. And one of the plot points revolves around the fact that the astronauts are exploring a planet that is orbiting not around a star, not around a white dwarf, but around a black hole. That is, an object that is so massive and so dense that the gravitational field of this object prevents anything from escaping, including light. So certain kinds of very massive stars, we think, when they run out of fuel, they collapse and become black holes. Gravity simply overtakes them, and they shrink down and become a mathematical point, a black hole. Now here in the movie, and probably in real life too, they're not actually totally dark, because in the immediate environment of a black hole, if it's pulling away matter from some nearby star, say, that matter swirls around and becomes very, very hot before it falls into the black hole. And during that hot phase, it can glow very brightly. And it's still far enough away from the black hole that that light can escape. So that's why the artists here have drawn this swirling vortex going around the black hole. And there's a planet here. And so that's an important plot point because time runs differently on this planet than it does on the Earth. So, do we know of any planets around black holes? That would be really cool. I would love to find a planet around a black hole. We don't know of any yet, I am sorry to report. But we do know of a technique that is capable of finding a planet around a black hole, even if it's totally black, even if it has no light whatsoever coming from it. We can figure out in principle that there's a planet going around it. That sounds totally impossible, right? If we're not getting any light from the star, from the black hole, how can we use the transit method? How can we measure the brightness of the object? How can we measure its Doppler shift? We're not even getting any light whatsoever. Well, the answer is a third technique that I haven't yet told you about, but that I would love to tell you about now. It is based on the principle of the mirage. And you all know what a road mirage looks like when you're driving on the highway and you have a long flat road ahead of you and it's really hot, so the pavement is very hot. You often see what looks like a pool of water or something very bright on the road ahead of you. That's a mirage. And the reason it happens is because the pavement is really hot and transfers some of that heat to the air immediately above the pavement. And hot air deflects light differently from cooler air. So a light beam going through air that is hot over here and cool over here won't continue in a straight line. It will instead be deflected, and some of those rays of light coming from the sky happen to be deflected up into your eyes while you're driving. And so you see the very bright looking sky as if it were on the road ahead of you. So that's the physics of a road mirage. The analogy, though, that I want to make is to gravity. There is such a thing as a gravitational mirage. And that's because a gravitational field, say from a star, will have a similar effect. It will deflect beams of light that pass nearby. So in this case, the deflection is due to the rising gravitational field as we approach the star. So a beam of light from a distant star, an unrelated star, that happens to be along the same line of sight as viewed from the Earth, those light beams will not travel in straight lines. Instead, they will be bent around and enter our telescope, producing these wild optical illusions in the sky, and in particular, magnifying the light from the background star. So the background star appears to get brighter as it drifts, or as this star drifts in front of this distant background star. If you want to know more about this, if you want to simulate this for yourself, you can actually use the bottom of a wine glass, the tapered glass bottom of a wine glass. You can either crack it off yourself and just be careful about it, or you can just, if you're If you're at a dinner at the Jewish Center and there's a candle at the table, you can just tilt up your glass and view the candle flame through the bottom of the wine glass, and it will produce the same sorts of optical illusions that are produced by this gravitational mirage effect. By the way, this is usually called gravitational lensing. I like the term gravitational mirage, but you more often hear it called lensing. So what you can do is if there's a light source or a black dot and you move this wine glass bottom in front of it, you can cause it to be split up into multiple images, and you can cause those images to be magnified. So that's interesting. It gives us a way to detect an object, that is the foreground star, independent of any light from that foreground star. All that matters is you have a light source in the background. So that's why it might work for black holes. So this is an animation to maybe make that point a little clearer. So here's our background star. It's emitting light in all directions. We're going to zoom out and watch a foreground star cross in front of it. Okay, so the idea is that Earth is over here. We are watching this star in the background, but this star and its planet are going to walk right in front and cause this gravitational mirage effect. And so what we're going to see is the light over time of the background star is going to go up and down because this guy's moving in front, but the planet will have its own additional effect. Oops, let me start that again. Okay, there it is, emitting light. Here comes the star and its planet in the foreground. And we see the light go up. And the gravity from the planet also introduces its own mirage and creates a little burst of magnification here on top of this larger effect from the star. So that's how we can detect a planet, even though we don't detect any light from it or from the star that it orbits. And this has worked. This is not just a theoretical technique. I don't know, at this point, probably like 50 planets have been discovered through this technique, through gravitational mirages or gravitational lensing. This shows you some real data from one of those cases where the brightness of a star, a totally random star that was monitored along with millions of others, this one happened to rise in brightness in this very characteristic way and then fade again. And then there was this additional dip that we can zoom in on here. That was due to the planet orbiting this anonymous star in the foreground. So this has worked to detect 50 objects. They are not, these are the hosts of these stars though are almost certainly not black holes. What you would want to see for a black hole is that the duration of this event would be quite a bit longer than this one here. It's the duration of the event that encodes the mass of the object in the foreground. And so if someday the people using this technique are able to see a very long duration event like this, and then they look really hard with a telescope and they see no light from the star that should be in the foreground, that would be pretty good evidence of a planet around a black hole. That's something to look forward to. All right, what about the end game here? Like, it's all very well to measure the mass of the planet, the size, the temperature, and so forth, but at the end of the day, we are going to want to see the planet. You're going to want to see a pale blue dot to channel Carl Sagan around some nearby star and not just some blip in a chart. And that would open the door to all kinds of other investigations too. If we could actually separate the light from the star and the planet in an image, we could obtain a spectrum of the planet, we could monitor it and see if its brightness changes as it rotates. All sorts of wonderful things would be possible. So how close are we to that goal of being able to see an Earth 2.0 in an image of a nearby star? Well, we're back here to trying to detect a firefly buzzing around a powerful searchlight from a distance of thousands of miles away. I said it was bordering on the impossible, and in fact, at the moment, it is impossible. We are not capable of making an image with high enough contrast to detect an exact copy of the Earth around a sun-like star in some distant star system. We can't do that yet. However, the method has worked in a few special cases. A few dozen planets have made themselves known in direct images. So for example, this is now a star field that contains the constellation of Pegasus. This is the Great Square of Pegasus for you stargazers, if there are any out there. And there is a star here along one of the sides called HR 8799. And if you look closely at that star, if you make a close-up image with one of the world's best telescopes, this is what you see. Don't get too excited. There's nothing here. There's just the star. Okay, there's a star, and then there's the glare from the star. Nothing on this image is the planet. This is the problem. We cannot focus starlight as sharply as we might wish because of the basic laws of optics. Some of the starlight always ends up spilling out and ruining the rest of the image and hiding any faint little dots that might be planets going around that star. Nevertheless, I have some very clever colleagues in this field who build specialized equipment to try to prevent the light coming directly from the star from reaching the camera, but allowing the light from any nearby planets to reach the camera. So they try to suppress the starlight and bring out any faint details that might have otherwise been hidden. It's called a coronagraph. So they use that, and this is the image that they got. So they were able to block the light from the star that's covered in this black circle here. Here, this yellow star is simply the location of where the star would have appeared. And it's not a perfect process. Even after a lot of fancy digital signal processing, there's still some rumble here in the background, and this little burst of light here, here, and here, and this little arc here. Those are just image artifacts from the imperfect ability to subtract the starlight. However, there are 4 other dots here. There's this one, this one, this one, and that one. Those are planets, definitely. And if you're wondering how we know, well, one way is just to keep making these images over the space of 10 years or so, and you can watch these planets move around the star. So what I'm showing you now is a kind of an endless loop of the planets moving over the space of, I think it's about 7 years in this animation. So we really are watching the other planets in a distant solar system going around their star, obeying the same laws of planetary motion that we see close to home. This is what it would look like if we were to approach this system in our spaceship closely enough to see these planets. We would have this same kind of view. So it's really stunning. It's a movie everybody should see. It's breathtaking. The reason it worked in this case, and not so much in most other cases, is because these are unusually massive planets that are unusually far from the star. So the equivalent orbits of Saturn, Uranus, and Neptune are indicated here now by these circles. So these planets are in the far reaches of this star system, and in fact 2 of them are even more distant than Neptune is around the sun. And they're all more massive than Jupiter. They're probably between 3 and 10 times the mass of Jupiter. So these are really gigantic planets. It also helps that the system is young. That means that these planets are still hot from the heat of their formation. Planets are born very, very hot. These are still not cooled off completely. That means that they emit more light than they otherwise would. So this system had a lot of things going for it, and that's why it was this success, even though most of the time this doesn't work. So what are we going to do? Well, what about this new space telescope you've been hearing about, the Webb Space Telescope that's just been deployed? It's going to start operating this summer in June. Everybody's really excited about it. It's going to do all kinds of wonderful things. Will this telescope allow us to see an Earth-like planet around a Sun-like star somewhere else in the galaxy? I wish it were so. It's not the case. Even this telescope, as amazing as it is, as many wonderful things as we're all looking forward to doing with it, it will not do that one specific thing. It needs to be more specialized than that. It needs to have one of these fancy cameras, this coronagraph, that is far better than the one that's going to be, that already is on the Webb telescope. So it will take not this next space telescope, but the one after that might be capable of doing the job. And so that one is one that only exists on paper and in daydreams. It will probably be something like the James Webb telescope, and it will have to unfold itself because it's too big to fit in the nose cone of a rocket and have this shield to protect it from any stray light. But it will be even more capable, probably 20 or 30 years off, given the way that these things work. But the people who have done simulations and trade studies and engineering studies to try and see what could reasonably be built, they really are aiming for lots of things, but in particular for this kind of image here, where they've blocked the light from the central star, and they would see the equivalents of Venus and the Earth and Jupiter. in a direct image. So that's where this field is heading. As I've tried to convey, there's a lot of progress. The frontier is advancing very rapidly, and I think you can expect to continue to hear about really interesting discoveries of new exoplanets, and we'll do our best to keep confirming science fiction as far as we can. All right, that's it, folks. Thanks for your attention. I will now look over at the chat to see these questions that have been coming in.
There are a number of questions in the chat. If you open it up, you'll see them.
Yep, got it. Let's see. So one of the questions is about unexplained aerial sightings or UFOs on which congressional hearings will be held. I don't really know much about those, to be honest with you. I haven't been following that whole story, except just from afar, just reading the same newspaper articles that you are. So I'm always, as I think we should be, quite skeptical of claims to have flying saucers that have reached the Earth using some kind of advanced technology and then somehow hiding from us for reasons unknown. But I don't know enough of the details about it to speak to your question, really. How will the James Webb Telescope forward your work? So it is going to do a lot of great things for exoplanets. It will be especially good at measuring these transiting planets, making very, very precise measurements of brightness, and also at learning a few things about the atmospheres of these planets through a technique called transit spectroscopy. So basically, when you take the spectrum of a star, you see the rainbow of light from that star. When a planet goes in front of the star, some of the light from the star filters through the planet's atmosphere on its way to us, and that can produce little features in the spectrum of the star, little absorption features. And if you detect those by comparing the spectrum before, during, and after one of these transits, you can learn about some of the molecules that exist in the planet's atmosphere, and Webb will be especially good at that. It will also has a coronagraph, and it's going to look for planets in direct images. It just won't be capable of going as far as planets as small as the Earth. Let's see. Does the Earth's global warming impact the moon or the solar system? I don't think so. No, because you have to remember, global warming and climate change is a very serious issue with a lot of potential implications for life on the Earth. On a kind of planetary scale, we're only talking about a couple of degrees Celsius. So once you step out from the surface of the planet Earth, and if you're not a creature that is very sensitive to the local temperature and the availability of water, it's really not an impressive planetary phenomenon. Let's see, have solar systems like ours been discovered? Yeah, I guess the answer is not really. The problem with detecting exact copies of our kind of solar system are that the Doppler and the transit methods both work well for really close in and really large planets. That makes everything easier. But in the solar system, the only planets that are close in are the small ones, Mercury, Venus, Earth, and Mars. And they're not even that close by the standards of a lot of the exoplanet systems. And there are some big, massive planets, but they're really far away. So Jupiter, for example, if we were looking at the sun from 100 light years away, trying to detect the planet Jupiter through the transit method, it would seem to be a cinch because the sun would get fainter by 1%. You can detect that with like a really good amateur grade telescope. So it's not difficult. However, the difficult thing is that only happens once every 12 years because that's how long it takes Jupiter to go around the sun. So you have to be very patient, and you'll need at least 2 or 3 of those events to be sure that it really is a transit and not just a glitch in the equipment. So the long orbital periods of the outer planets make it quite difficult. So the answer is we have detected enough planets to know that something like a third, maybe a half of sun-like stars have the sort of planets we can detect. Big planets, close-in planets. But that leaves the other half to 2/3 of the stars. They probably have planets, but they're just too small or too distant from the star for us to detect with our current technology. Let's see, what else do we have here? We enthusiastically imagine distant stars and planets and exoplanets. Is there any suggestion that the infamous warp speed to travel to these distances is theoretically possible? Yes, so warp drive and wormholes, very important for science fiction. You can't get anywhere in the galaxy without them, right? You can only write so many stories about an intergenerational spaceship that takes 10,000 years to get to Alpha Centauri. You really want to get there for your characters to get there fast. But there the news is all bad. Like there is no indication in the laws of known physics that wormholes really exist or would be stable or would arise naturally in the universe, or that warp drive is possible. As far as we can tell, the speed of light truly is the maximum possible speed for anything to travel. So I'm afraid there is one thing I can say. That in the movie Interstellar, there was this plot point that the astronauts landed on that planet. It's a very strong gravitational field. Then they came back to the Earth, and everybody on the Earth had aged like 70 years, and they had only aged a much smaller amount of time. That is actually real. Okay, that is orthodox, well-tested physics. That is one of the principles of Einstein's theory of relativity. And the same thing would happen if you were traveling very fast. You don't just need a strong gravitational field. If you took a rocket ship and you traveled very close to the speed of light and went out to Alpha Centauri, and then came back in the other direction and came back to the Earth, it really is the case everybody on the Earth would be much older than you would expect based on when you left and how far you went. So that is real. So it's, in that sense, it's easy to travel into the far future. Easy. All you need to do is travel close to the speed of light. But as far as we can tell, you can't beat that limit and you can't go backwards in time, either of which would be helpful for science fiction. Does the gravity of a white dwarf change as it goes from a red giant down to a white dwarf and further into a black hole? So just to be clear, the white dwarf doesn't become a black hole. Black hole is only the fate reserved for very massive stars, maybe 20, 50, 100 times more massive than the sun. Those are the ones that become a black hole. Stars like the sun become red giants, then they puff off their outer layers and become white dwarfs. And those, as far as we can tell, are stable forever. There's no reason why they would collapse. They're immortal, basically. They can withstand the gravitational force forever. Does the gravity change, though, during this transformation? It does, mostly because you lose all the mass of those outer layers, and so you end up with a star that is less massive than the one you started with. And that has the kind of non-obvious effect of causing any planets orbiting it to have their orbits widen. They get farther away from the star as it loses mass. So I think that's the only major effect, the only one I can think of at least. Didn't Einstein prove that light bends around a gravitational field? I would say Einstein hypothesized it. He had a very good theory that if you took his theory seriously, light should be deflected by a gravitational field. And it was after his theory was published that it was confirmed by looking at the positions of stars very close to the sun during a total solar eclipse, which is the only time when you can look for stars right in the vicinity of the sun. And the positions of those stars showed that the beams of light from those stars had been deflected by the sun's gravity. So yes, Einstein is very closely connected to that whole story. Do we use radio telescopes? Not really. So I wish we did, because I was originally trained as a radio astronomer, but so far that has turned out to be irrelevant. There is one exception. So there is one star that is emitting a lot of radio waves in a very peculiar way. And it has been proposed that it's because there's an orbiting planet. And the planet is so close to the star that their magnetic fields interact with each other in such a way as to produce radio waves. That has not been confirmed. We haven't seen the planet yet, for example. But if it is, that would allow us to use radio telescopes to study exoplanets for the first time. Is it possible to conceive of a telescope, even if no such telescope exists, that would help us detect or better understand dark matter? Okay. Dark matter. So that's an interesting topic. That is some kind of matter which we're pretty sure exists because we see its gravitational effects throughout the galaxy and in other galaxies. But whatever it is not glowing, and it's not made of any kind of a normal material. So that is the mystery of the dark matter. which I haven't mentioned yet, but it is very interesting. Could we see a telescope? Could we build a telescope that would be sensitive to dark matter? I guess the answer is yes, in that gravitational lensing has this virtue that it allows you to see things that are not glowing. And so that is one of the methods that we have to demonstrate that dark matter exists, is when we see a galaxy in the foreground producing this gravitational lensing effect on the galaxy in the background. The size of that optical illusion tells us how much mass is in the foreground galaxy, and it's often a lot larger than the mass that we can attribute to stars and ordinary things. So that's kind of like having a telescope that allows you to see dark matter. I think that's probably the best we can do right now. If white dwarfs are immortal, would that mean the ultimate fate of the universe is that it will end up populated entirely by white dwarfs and black holes, since they don't get to be recirculated to make new stars? I think the answer is yes. So now that we are fairly sure that the universe is expanding and will continue to expand by all the evidence we have so far, it will not recollapse. That means in the far, far future, all the galaxies will be very spread apart, and the stars will burn out and either become white dwarfs or black holes or neutron stars, which is this kind of thing in between those two categories. And as far as we know, those things are stable. So they would last not just billions of years, but trillions of years. Now that could be wrong. It could be that, say, it turns out the proton or a neutron, or proton is unstable after 1 trillion years. And so maybe everything would end up decaying. But according to the known laws of physics and what we know about particle physics, the universe really will be populated by these stellar remnants, we call them. Good questions. Any more?
That was great. I actually now, when I stargaze, I have new respect for what I'm looking at.
Perfect.
And I'm convinced that there is a parallel world out there somewhere, another Earth with life on Earth, but who knows? But it's absolutely fascinating. So I thank you for this amazing presentation.
Thanks.
It was wonderful, and I learned so much about stars and planets. And I'm going to continue to watch Star Wars and every science fiction planetary movie. So thank you so much, Josh. This was great.
My pleasure. Thanks for coming out, everybody.
Thank you, everybody, for your great questions. And I know we're all a lot smarter tonight than we were before we started. So I'd like to say good night to everybody. See you in the fall with a new series of Great Minds Salons. It's been a pleasure. Thank you so much to all of you.
Thank you, Ellen.
Thank you.